All right, let's pull back the curtain on one of the most incredible magic tricks happening inside your computer every single second: multitasking. I mean, really? Have you ever stopped to think about it? You've got your browser open with like a dozen tabs, a video playing, your chat app is going off, and you might even have a game running in the background. How in the world does your computer keep all of that straight? Well, the answer starts with a pretty fundamental conflict. So the whole issue really boils down to this. Your computer has a fixed physical amount of memory. We call it RAM, maybe 8, maybe 16 gigabytes. But our appetite for running programs, it feels practically infinite. So how do you fit an ocean of programs into what's basically a coffee cup of RAM? The answer is you don't. Instead, your computer's operating system creates this brilliant illusion. It essentially tricks each and every program into thinking it has this huge private playground of memory all to itself, even when it's really sharing a very, very crowded space. And the secret sauce here, it's not some kind of super exotic technology. It's actually a very practical, very clever idea. Instead of trying to cram an entire massive program into that precious RAM all at once, the system only brings in the specific little bits and pieces it needs at that exact moment. And this amazing idea, it has a name: virtual memory. You can think of it as the master illusionist. It lets programs believe they have this massive, perfect stretch of memory to work with, while behind the scenes, the operating system is frantically shuffling all the little pieces between your super fast RAM and your much, much slower hard disk. Okay, so how does the OS actually pull off this incredible sleight of hand? Well, the specific technique is something called paging. And this is really the core mechanic of the whole magic trick. So here's how it goes down. Imagine your RAM is a small kitchen countertop, and your hard disk is a giant pantry. You just can't fit everything from the pantry on the counter, right? So paging breaks your recipes, which are your programs, into these little fixed-sized instruction cards called pages. You only bring the cards you need right now onto the countertop, which itself is divided into little slots called frames. And the OS, it's the head chef, constantly deciding which recipe cards get to be on the counter at any given moment. But here's the catch in our little kitchen story. What happens when the recipe calls for an ingredient, but the card for it is still way back in the pantry? The whole cooking process has to grind to a halt. In the world of computers, this is called a page fault. It's basically an alarm bell that rings telling the OS, hey, the instruction card I need isn't on the countertop. The OS then has to stop everything it's doing, run over to the hard disk, our pantry, find that missing page, and bring it back into RAM. And the cost of this interruption is just staggering. Getting data that's already in RAM takes nanoseconds, billions of a second. But dealing with a page fault, that takes milliseconds. Now, that might not sound like a big deal, but a millisecond is a million nanoseconds. In computer time, that is an absolute eternity. It's the difference between grabbing a spice right next to you versus having to drive to the grocery store to go get it. Now, a few of these trips to the pantry are no big deal. But what happens when you try to juggle way too many recipes at once? Well, this is where our clever little trip can start to spectacularly fail. You see, the operating system has this really noble goal. It wants to keep the CPU, the brain of the computer, busy at all times, because a busy CPU means a fast, responsive computer for you. So it tries to cram as many programs or processes into RAM as it possibly can. This strategy is called increasing the degree of multiprogramming. And at first, this works beautifully. As we add more and more programs, the CPU finds more useful work to do. Its utilization, basically how busy it is, goes up, and our whole system feels faster. Everything is great. But there is a tipping point, and when you cross it, things don't just slow down a little bit. They fall right off a cliff. I mean, just look at that drop. After a certain point, adding just one more program causes the CPU's performance to absolutely plummet. Your computer basically grinds to a halt. What on earth is going on here? This catastrophic state has a name, and yeah, it's as ugly as it sounds: thrashing. This is the exact moment our magic trick completely and utterly breaks down. Thrashing is what happens when the system has so many programs jammed into RAM that none of them have enough of their pages to actually do their job. So what happens? Almost every other instruction causes a page fault. The OS ends up spending all of its time just swapping pages back and forth from the hard disk. Our chef is just running to the pantry over and over again without ever actually cooking anything. No useful work gets done. Okay, so let's imagine we avoid thrashing. We're running smoothly, everything's fine. There's still another, much more subtle performance problem that's baked right into this whole system. A 2x slowdown on every single axis. So here's the crucial part. For every single piece of data the CPU needs, it actually has to go to RAM twice. First, it has to look up the data's physical address in this big index called the page table, which is also in RAM, and then it has to go to that address to get the actual data. That's 2 trips to memory for just one piece of information. Now, this two-step process would make our computers feel sluggish all the time if that was the end of the story. So engineers came up with one last brilliant piece of hardware to solve this final puzzle and make the whole system absolutely fly. It's called the Translation Look-Aside Buffer, or TLB for short. The TLB is this tiny, ridiculously fast piece of memory that lives right next to the CPU. It acts like a cheat sheet, or a cache, storing the most recently used page translations. So instead of our chef having to look up every single ingredient in the giant cookbook every single time, they just keep a little post-it note of the common ones right there on the counter. And the performance impact is just huge. If the address the CPU needs is on that little cheat sheet, that's called a TLB hit, the whole process takes only about 60 nanoseconds. But if it's not on the cheat sheet, a TLB miss, we have to do the full 2-step access through regular RAM, which takes almost double the time, around 110 nanoseconds. And here's the real kicker. Because of a principle called locality of reference, which is just a fancy way of saying that programs tend to reuse the same data over and over again in short bursts, the TLB hit ratio is typically over 90%. That little cheat sheet is right almost all of the time. And that is why our computers feel so fast, even with all this incredibly complex memory magic happening under the hood. So, when you think about it, from the grand illusion of infinite memory to the catastrophe of thrashing, and finally, the little bit of hardware genius that makes it all fast, it's an incredible story. It really makes you wonder, if this is the magic it takes just to manage memory, what other amazing, complex illusions are happening inside our devices that we just take for granted every single day?